So to generalize out the binomial expansion, simply this. If I call the coefficient NCK, okay, so NCK is going to be the coefficient of x to the power of k in 1 plus x to the power of, that should be n, by the way. A bit of a misprint there. Pretend it's an n. Okay. Now, we sometimes see this notation. When we're dealing with binomial theorem, instead of the traditional NCK, which we see in combinations, permutations, combinations, binomial theorem, we often write it just like this, where it's two parentheses. It's not a fraction, but just the n on the top and the k on the bottom. So you might see that notation a lot in binomial theorem. Doesn't mean you have to use it, as I haven't done here. So 1 plus x to the power of n would be nc0 plus nc1x plus nc2x squared, and so on and so on and so on, up to x to the power of n. Which I could extend to, instead of 1 plus x, I could have a plus b. And it's like I was saying before. We'll start at the power of a, it'll be n. Powers of a will go down by 1. Powers of b will go up by 1. Those powers will always add to give n, whatever n happens to be. So if I want to expand out 2 plus 3x to the power of 4, then it would be 4c0 to the power of 4, 4c1 2 cubed, 3x, and so on and so on. So powers of 2 going down by 1, powers of 3x going up by 1. And then I just substitute in for 4c0, 4c1, and so on. Now, how you work out 4c0, 4c1 is up to you. I guess it depends on how big the number is. See, power of 4, you might remember just Pascal's triangles row, or you could go to your calculator. It is the same notation because it is the same thing. So some wonderful relationships then in the triangle, thanks to perms and coms. To work out any particular coefficient, NCK, we go to the row above. And that's what this one's saying. If I want to work out NCK, then the row above would be n minus 1, and I would get the k minus 1th and the kth and add them together. So here's a proof of that, if you like. So 1 plus x to the power of n would be 1 plus x times 1 plus x to the n minus 1. If I was to write out 1 plus x to the n minus 1, I would get n minus 1 c0, n minus 1 c1x, and so on and so on and so on, until I get to the last term, n minus 1 c n minus 1 x to the n minus 1. Now, I want to just look at the coefficient of x to the power of k. On the left-hand side, in 1 plus x to the power of n, it would simply be nck. On the right-hand side, I'd say, well, the 1 would have to be multiplied by the term that has x to the power of k, and the x would have to be multiplied by the term that has x to the k minus 1. So on the right-hand side, the coefficient would be 1 times n minus 1 c k minus 1, and then the coefficient of x here is 1, so 1 times n minus 1 c k, and there we have it. So that's a little proof there of our relationship. Okay, the second relationship is what I was just saying about the symmetry of the triangle. So NCK will always equal NCn minus k. So the end ones equal each other, 2 in equal each other, 3 in equal each other, and so on. We have symmetry about our triangle. And the third one is just saying each row begins and ends with 1. So NC0 and NCn will always equal 1. Okay, so 5b we'll have a bit of a play with.